Okay, why do some guns have more recoil than other guns? You already answered one. Go. You put your hand up. It counts. Okay, I like all that. So what do you mean by bigger explosion? Okay, if the explosion is bigger, the bullet coming out is faster or slower? Okay, faster. So you said it correct. Where's momentum is conserved? If the bullet comes out faster, finish that sentence. Yes, I totally Put a period in that, and that's a sentence. Maybe. As long as you have a pausing of your clause or whatever. I'm not an English major. That is correct. The bigger the explosion, the faster the bullet. The bullet has more momentum. Momentum is mass times velocity. So you make a heavier bullet, right? You hear stories about people like the Dirty Harry gun, the Magnum 44 or whatever, has a big, huge chunky bullet. People like break their wrist shooting this gun because the bullet is so big that the gun has to recoil, right? Before there's no momentum, I pull the trigger and explosion goes off. Afterwards, the bullet goes flying this way really freaking fast. So I have to have the same amount of momentum coming back the other way to make them add up to zero, to make them cancel out. And that stuff coming back the other way is your hand and the gun. It goes shooting back. What's up? I think that's just your hand. And I mean, if you think about, well, yeah, like you're holding the bottom of it if you, right, it's like a torque type thing. What's up? No. I think the effect that the expanding, no, I don't think so. Yeah, that recoil has to go somewhere. Right? So if you want to shoot a big freaking bullet, you gotta have a big freaking gun, or be ready to go fly across the room. Same thing with okay, this is what I mean. In action movies, when it's like the big silver, it's always silver for some reason, the big silver handgun, he like shoots the guy and the guy goes like flying back through a plate glass window. Right? Like whoever you kids are watching nowadays in action movies. In my day it was Arnold Schwarzenegger, the Governor, who was in charge of this state. Think about it. Would pull out the gun, like shoot the guy, and he would and go flying back like up onto a car. Okay, well, I don't mean to break your heart, but like right, we just experimented that away, right? Unless when Arnold shot the gun, he went flying back up onto a car. The guy getting hit by the bullet is not going to go flying up onto a car. Tight. Same thing with I think Professor S talked about the little guy from Guardians of the Galaxy. Yeah, the little what's his name? Rocket Raccoon. When he shoots a big rocket and hits some guy and knocks him in the next week, it's a raccoon. Okay, whatever. He would have to go flying back to conserve momentum. Okay. Next question. One of Einstein's most famous equations is E equals mc squared. The caret means squared. Does this mean that energy can be turned into mass and vice versa? Oh, okay. I guess if you're good at test taking, you see it. Yes. Give examples of both. You cannot give examples of both if that was not possible. So evidently it's possible. Give examples of both. Ready to go. What's up, Doug?
So you and I are debating about whether or not we can think of ionization, like an atom, you ionize an electron.
Energy to mass.
Is that energy to mass? Like, I've never heard of a difference in mass between products.
There would have to be, right?
There has to be? Why?
In terms of like, okay,
So overcome the binding energy and then you have some kinetic
so
energy.
yeah.
That's all there is to it.
Well, but this is the thing that like I don't like thinking about things in terms of like separating like energy and mass. Like when you start doing, for me, I've just been trained like the last few years to think about energy and mass being totally equivalent. And so like to me, it's like yeah, there's more mass there. There's more energy there. But they have the same fucking units. You know, like
Yeah, but so when let me ask a more direct question.
really quickly.
What? I just didn't check really quick. If we do 3 questions, we doing that like to you, or we doing that in groups?
We can do it. Well,
Like we're gonna do the last 10 minutes just to be
Yeah,
last.
we keep it is. Also, like, and if they don't have questions, maybe we should keep some relativity and cosmology questions. I like that.
I
We
don't
can
say cosmology for last.
Yeah.
Ask me after.
Sorry.
No worries. That was more important.
What's up? Yeah, like these. DC, wait, and UV. Yeah. Yeah, we were before. Yeah. Oh, okay, awesome.
So now they just have. Ooh, this one.
Sweet.
How do you? Let me get back to.
Okay, last few minutes. Okay, we have not talked a lot about cosmology and special relativity. In the last that clock is fast. In the last 15 minutes, we open the floor to like any outstanding questions people have about anything we've talked about or anything from the class that Professor Solar said you'd have to know. If you don't have to know it, we'll tell you right now. Like you don't have to know that. Good question. Ask us later. But we'll open the floor. If there aren't any super interesting questions, we'll talk a little bit about cosmology and special relativity. Okay. Any questions? Go. What's up? The difference between special and general relativity. It's a great question. Special relativity has to do with motion at constant velocity relative to someone else. Right. So the example that I think of when I think of special relativity is you're out in deep space. You're in the old style MTV Video Music Awards, like moon suit. You're out in deep space. There's no stars around. It's very dark. You have a little flashing green light on your spacesuit. All of a sudden, you see another astronaut chick come floating at you with a little red light flicking on her, spacesuit. You both just pass each other. Like, hey, you wave as you go by. Who's moving and who's standing still? Like, you have no way of knowing. That's special relativity, right? There's no experiment I can do to decide whether or not I'm moving and she's standing still, or she's standing still and I'm moving. They're all equivalent, right? So to say that I'm standing still and she's coming at me, it's the same as saying that she's standing still and I'm going at her, right? From a special relativity, general relativity comes to it concerns accelerating. So in that case, with the spacesuit, if I was speeding up or slowing down or taking a turn, I could feel that because I could feel an acceleration, right? So this is special relativity is motion at constant velocity. And the weirdness that happens when you start going almost as fast as the speed of light. General relativity comes from accelerating reference frames, and the fact that if you wake up in a room with no windows, but you stick to the floor because of gravity, it could either be gravity or you could be in a rocket out in space accelerating, like at g, at the acceleration due to gravity. And there's no experiment you could do to decide between the two things. So as far as we know, this building is not on Earth, it's in deep space in a rocket accelerating at g, at 9.8 meters per second squared. There's no experiment we could do, chemistry, we could raise cattle, we could watch an old tiny color area, black and white movie, nothing we can do to decide whether or not we're out in deep space accelerating up at g or sitting on Earth in a uniform gravity field or whatever. That's general relativity. Cool. There's a question over here. How do X-rays see cancer cells? You mean like why do we use X-rays to treat cancer? I don't know. Eric, did you write that? Eric, the cancer reflecting more X-rays than, was that one of your practice ones?
Yeah. So cancer, the tumors will under an X-ray absorb some X-rays and have the shadow as if it were a bone, right? It's not to the same extent.
Do you know why?
Why?
Yeah. Is that a density thing or is it composition or? Okay.
It's complicated.
It's complicated. But yeah, tumors will absorb more X-rays than healthy tissue and appear as a shadow in an X-ray like similar to bone. Any other questions from anything in the course ever? What's up? Black body radiation. Yes. So a bunch of really old white dudes that are now dead did a bunch of experiments a long time ago, and they discovered that when there's this theoretical thing that we came up with because we need easy things to talk about, and this thing is easy, or it's very, what was one thing of? It's very concrete what I mean. When I say I have this object and it absorbs all light that hits it, that's what I call a black body, right? It absorbs everything that hits it. So it doesn't, right? It absorbs radio all the way up again, right? It absorbs everything in the electromagnetic spectrum. That's what I call a black body. And by doing various flight experiments and actual experiments, it was discovered that black body, the radiation coming off of a black body, right? The light that comes off of it depends on the temperature of this black body. So a very cold black body will radiate more and more redder light with a longer and longer wavelength. And the hotter this black body gets, the more blue the light gets, or the shorter the wavelength it gets. So when I say red and blue, this is like a very abstract red and blue. I don't mean that it gets like bright, like fingernail lipstick red. When I say something gets redder, it gets a longer wavelength. So that means if it was emitting mostly in like microwave, which we can't see, it's too long a wavelength. If it gets redder or if it gets a longer wavelength, it drops down to, like radio. Right? So it gets a longer wavelength the colder that gets. If I heat up my black body and keep getting it hotter and hotter and hotter, it gets bluer or it gets shorter wavelength. Right? And so that bleeds down into a ton of physics and a ton of cool things in, like our daily lives. Like, why is our sun yellow? Why isn't our sun blue? Like, well, because our sun has a certain temperature. If the sun were a lot hotter, it would be bluer. Is that kind of like, okay. Any other questions? Because it, like, yeah. Yeah, I think, yes. Okay. That's a really good explanation. If it is, Like if a black body is not emitting anything, and I start shooting a bunch of radiation at it, it's absorbing everything. It starts heating up because it's absorbing. It has to take this energy and put it somewhere. So it takes this energy I'm hitting it with and turns it into heat. As it starts heating up, it starts emitting more and more and higher energy. Right? Eventually, it reaches a spot where if it were to emit any more energy, it'd be emitting more than it was absorbing. So it reaches this equilibrium of it's absorbing all that it can, but it's emitting all that it can, and these two things equal out so that it stays at the same temperature. Right? If it were emitting any more, it would cool off. If it were absorbing any more, it would heat up. That's really good. Yeah, thank you, Suga. What's up? Like so, a black body, as far as like a physicist would talk about, is the same thing as like a frictionless plane and like no air resistance, or or like a spherical cow or whatever. So these are like theoretical things that we talk about. An example of like a good, a spherical cow, right? If you're modeling a cow, you start with a ball. Think about it. Examples of black body, like.
So, I mean, actually, like in the context of this class, you don't really need to come up with an example of an exact black body.
Yeah, because there's not one.
Because the takeaway from black body radiation is that the type of radiation that's emitted by a thing depends on its temperature. The spectrum of radiation depends on the temperature. And you are clearly not a black body. You look peach, which is very distinctly different from black, or maybe you look darker or something like that. But like maybe you got a tan, or like maybe you're African American or something. But you're not black. You're not a black body. So you have some temperature, you emit some radiation, right? And that radiation depends on your temperature. So even though you're not a black hole, you still emit black body radiation in the context of this class.
Yeah, so kind of like everything is a black body, kind of, and nothing is for this class. Like you have a certain temperature, you emit in a certain like wavelength band, just like a black body would. What's up? Tunneling. Is that on here? No? Oh, it was. Tunneling. Yes, okay. So the example that I always use and I think about is if I were to make some like cool Dr. Seuss spinny like shoes on a wheel, like just kick soccer balls. There's like just a machine that kicks soccer balls at the same speed every single time. It kicks a soccer ball at the exact same speed, and I point it at like a hill, this grassy fork on a hill or whatever here, and I calculate at the speed I give the soccer ball, it can roll halfway up the hill and roll back down. Right? In 1,000 years, a ball will never reach the top of the hill. The soccer ball will roll halfway up and roll down. If I made the same machine with electrons, kicking electrons up a hill, now because this quantum world takes over and quantum phenomena like has there's a probability that randomly this electron will not just stop halfway up the hill and roll back down. It'll fluctuate and randomly get enough energy to make it to the top of the hill or and over the hill. Right? So that's what's called tunneling. It seems like it only has enough energy to get halfway up the hill, and it tunnels through the hill and ends up on the other side. Even though what's kind of happening is it's spontaneously getting enough energy, like randomly through random fluctuations, to like make it over the hill to the other side. So that's kind of like a general, like very rough conceptual idea of what's going on. Like the way we use that in our daily lives is that this happens very quickly, and so we use that in like electronic devices that we can control how fast this electron will tunnel, like the probability, by like varying what we're kicking it with and like what it's trying to go through. And so if inside your cell phone or your computer, the probability of the electron to go through is almost zero. Then if we change a little bit of electricity or a little bit of voltage, now the probability goes closer to 1. As soon as that electron jumps through, the computer can do something. Kind of. So it's like taking an old-timey switch that would like have to switch electric like current in like an old computer. In a new computer, it's whether the electron like jumps. So we're taking it from a bunch of electrons, switching electricity on and off to like one electron just quickly going through a tiny little hill. And that means that like that's why computers got smaller. That's why we have cell phones that are this big, not this big. It's tunneling predictable. It's random. It's not deterministic. So I can't tell you with absolute certainty. I can really only give you probabilities. And over a large number of samples, I can say, out of 1,000,000 tries, 900,000 electrons will go through, and 100,000 electrons won't about. But I can't tell you this electron will or this electron won't, kind of thing. So it's not a deterministic thing. It's more random. So over a large sample size, you can say about how many will happen, but you can't say like trial by trial what will happen. Can they tunnel? Because energy is quantized for them. So why can't we tunnel? Actually, we could. Someone calculated that it would take like